All right, everybody, welcome back. Hope everyone had a wonderful Thanksgiving. So today's lesson is just kind of a review of sorting. There's a few segments that take you through just sort of an overview of the different sorting algorithms that we've talked about. And then there's a new sorting challenge to solve as the homework problem. We talked a little bit about how that works, which is selection sort, which is a sort that we haven't typically done in 125, but I actually think there's kind of a neat parallel with insertion sort there, so we decided to do it. All to say that I don't have a huge amount to talk about today. We also do go into a little bit about how to actually do practical sorting in Java. Sorting is, there's this kind of like, learning computer science and what you do in real life are not always fully aligned. There are things that we teach you to do, and we want you to understand along the way that you are not expected to do on a real project. Again, if you needed to sort something and you were working for a company or on a project or at a startup or whatever, or even on a hobby project, and you decided to implement your own sorting algorithm, that would really just be a big waste of time. Even if you got it right, which you might not, the sorting algorithms that are built in to most modern programming languages are far more sophisticated than the one that you would probably be able to complete and more well tested. And so the typical thing to do when you need to sort something is call a method that does that. So we talked about a couple of those, and then we talked a little bit about how to sort objects in Java, which is something that, we have this, we talked a little bit previously in the course about how to use objects to model data. Frequently those fields in the objects that we create up to do data modeling map onto some attribute of the data. And frequently when we're working with data, we want to sort things in one of several different ways. So we might have a object or a model that has a couple different keys or a couple different fields, and we want to sort based on one field at one point and another field at another point. And Java has some nice built-in ways of doing that. Although they start to get a little bit, I shouldn't say complicated, there's nothing complicated about it, just they introduce some new ideas that we haven't seen before. So that's kind of fun as well. All right, so I think that's about all I have to say. Happy to take questions about what's here. We can go through any of the examples that you guys would like to see. Actually, one thing I'll do maybe while I'm waiting for people to is see if I can find the actual source code for collections.sort. Let's see here. Okay, so this looks like it just uses arrays.sort. So what we want is arrays.sort. Okay. Just wanted to see what's actually in here. I don't know how old this would be. Let's see. This looks like it's from 2015. Okay, that's relatively recent. Let's look for the sort function here and see. Okay. So this looks like it is using something called dual pivot quicksort. Interesting. Dual pivot quicksort. Let's look this up. Try to find out more about this. I thought that Java used timsort, but maybe I'm wrong about this. Dual pivot quicksort. Okay. Maybe this is a future CS125 homework problem. Interesting. Don't know why you would use, what does it say here? It says this algorithm offers, okay, so it's claiming that we still get O(n) log n, which remember is what we want on many data sets that cause other quicksorts to degrade to quadratic performance. That's O(n) squared. That's what we don't want. Right? Remember, so Quicksort has this feature has this liability where depending on the pivot values and how they partition the array at every step, we can do as well as, you can do as well as merge sort while requiring much less space, or you can do as poorly as an O(n) squared sorting algorithm, even something like bubble sort. And so it's the choice of these pivot values. And again, it looks like the what's being used. At least this is the Open JDK, and this was as of Open JDK 8. But it looks like this has been modified fairly recently, and so this is probably pretty similar to what's being used. Again, I had thought that Java was using Timsort, was one of the languages that was using Timsort, which has a fair amount of additional complexity that's part of it, due to how it approaches things. But I'm sure we can find source code for that somewhere, but I'm not going to hunt around it for too longer. Yeah, okay, so let's go through that. Let me pull up some of my old slides here, which will be helpful. Okay, so let's look at Quicksort, and let's look at worst case, right? So here's a worst case. I don't know if I ever even did this. So here's a worst case example for Quicksort, right? This is Quicksort. First value is the partition. So I choose the first value as the partition. Remember, with Quicksort, what we want is a pivot value that partitions the array evenly. But that pivot value is also known as the median. The only way to figure out what the median value is for an array is to sort the array and then find the value that's in the middle. And what we're trying to do here is sort the array. So we really have no way of picking the appropriate pivot value. We have to guess. There are some guesses that are better than others. Choosing a value at random might be better than just choosing the front or the back, because when we choose the front or the back for Quicksort, we do fall into this problem with sorted arrays. So here's the problem. So I choose 8 as the pivot value. And, I pivot the array around 8, but how much of the problem do I still have left to do? So now I've taken an array that was size 8, and I have an array that's size 7 left to do. And this keeps going in every step. And so the problem here, let me see if I can find the performance comparison, right? So this is the worst case, right? So the partitioning step is on. This is similar to merge sort, right? So you can really kind of think about these two similarly. Merge sort, the merge is on. In Quicksort, the partition is on. The amount of space they use is different, but runtime, we're just thinking about, time complexity here. So merge sort, merge on, Quicksort, partition on. So the question is, how many of these operations do I have to do? With merge sort, I like to think about it from the bottom up, where we start with the small arrays of size 1, and we build them up, because that tells you how much we sorted at every step. So after one set of merges, I break everything down until I get arrays of size 1. This is merge sort. Then after one set of merges, I have sorted arrays of size 2, 2 sets sort arrays of size 4, 3 sets sort arrays of size 8, 4 merges sort arrays of size 16. So at every step, it's doubling. And I do that until the size of the sorted portion is bigger than the amount that I started, at which point I'm finished. With Quicksort, it's a little bit different. So Quicksort is actually sorting on the way down. So the question is, how many partitions does Quicksort have to do before it gets to arrays of size 1, which are already partitioned, right? So if you think about it, if let's say I partition the array evenly at every step. I start with 8, then I go 4, 2, 1, 3 partitions. But if the pivot value doesn't partition the array evenly, then what can happen is I can start with 8, 7, 6, 5, 4, 3, 2, 1, and I end up having to do n partitions. And that's where I get n squared. So if the pivot value does not partition the array evenly, I can require more steps than I would normally. And this is why, let me go back to one of the previous lessons here. It's a great question, by the way. Let's go back to Quicksort, and let's look at the performance analysis, right? And so how did I actually do this? Let me kind of fast forward to the end here, where we actually put in our, So now, okay, so sorry. So this was, I think I'm setting this to a random int array. And if I run this a few times, what you'll see is that the performance bounces around. It's not constant. With merge sort, it would be identical every single time, right? And if I don't reassign values to be a random array, you see that it's the same every time. So given the same, Quicksort's not a random algorithm, right? There are what are called randomized algorithms where there's randomness built into the way the algorithm works. Those algorithms can actually be very efficient at solving certain types of problems. But Quicksort's not a random algorithm. So given the same input, it will always take the same number of steps, right? Assuming that the implementation doesn't change. What's happening here is I'm giving it random data. So you'll see the code that we're working with, I'm giving it random values at every step, and I'm asking it to sort the array. And as a result, you'll see, the worst case here is with sorted data, so that takes 35 steps. The best, the average case when I'm using random data, sometimes it's around 20, sometimes it jumps up to the high 20s, sometimes it's as low as 17 or 19. I think it looks like 17 is like the minimum. You could run this like 1,000 times and see what the minimum value is. I think it's probably about 17. So the idea here is that, depending on how the pivot values partition the array, Quicksort's performance can vary. And what really depends is the number of, what really gets affected is the number of partitions I have to do. Does that make sense? It's a great question. And again, let me go back to, this example again, because I think this is the good one. I didn't do either one of these out fully because they're kind of tedious to make. But again, so visually what we can see happening is that every time I partition, the array only gets, the amount I still have left to work on only gets one smaller. And so it's going to take n partitions to fully work my way through the array. Another way to think about this, right, is to compare it with like insertion sort, right? But imagine that I'm growing the sorted part of the array on the right? So I take 8 and I move it into the sorted part of the array. I take 7. So essentially this is behaving like insertion sort. And insertion sort, similarly, the worst case is I can have bad cases with insertion sort where the data is sorted backwards because I have to drag everything to the front of the array every time. So the pathological case here for Quicksort is when the data is already sorted. Now, again, this depends on the pivot value. So Quicksort is one of these algorithms that you have to be a little bit more specific. Merge sort always works the same way. Quicksort, there are different approaches to choosing the pivot value. If I don't pick the pivot as the first value, then I can do better. Then it's not clear that that this is a worst case. So if I pick the pivot value as like the midpoint, then I'm actually going to do really well. So imagine that I have sorted data and I pick the midpoint as the pivot value. Well, now that value is going to partition things perfectly. And so I'm going to get really good performance. And I suspect that real Quicksort implementations probably avoid choosing the first value or the last value as the pivot simply because those approaches are very, very susceptible to this problem, right? I can choose any value as the pivot value. It doesn't matter, right? You guys have implemented partition. If you think about how you did that, we asked you to partition based on the first value. But if you want to partition based on a different value, you just move that value into the first position, and then the rest of the algorithm is exactly the same. So Quicksort ends up, the conversation about Quicksort very quickly becomes how do you pick a good pivot value? First value, last value, typically not considered good pivot values. We have to implement sorting algorithms. So this week's quiz has no sorting related coding on it. There are multiple choice questions on sorting. There may be a sorting question at some point in the future. If there is, it will be similar to stuff that you've already done. On the other hand, if you think about it, we're not asking questions on we're not asking programming questions on quizzes that are things that you've seen on the homework, not directly on the homework. We used to do that in the past, but in the past, when you were doing the quiz, you didn't have access to your homework answers. So this is a little bit of a different situation. So, and at this point, you've implemented bubbles. We've implemented bubble sort together. You've implemented insertion sort as a homework problem. You're implementing selection sort today. We've implemented merge together, and you finished merge sort. You implemented Quicksort partition, and we implemented Quicksort together. There's not a lot left to ask, right? I'm certainly not going to throw like a strange type of sorting question on the quiz. I don't expect you to. There are many, many different sorting algorithms out there. And it can be fun to kind of pick some and figure out how to implement them, but that's not something that I would expect you to do in a quiz environment. Yeah, no, that would be strange. It's also, I mean, sorting is one of those questions. It's a little, you've seen us have to go to some lengths to try to make sure that you're doing the right thing, right, when you sort something. So today's problem, returning a list of the values that you identified as the minimum, that's a weird thing to do. Like a normal sorting algorithm wouldn't do that. But at the same time, I can't just ask you to sort something, because if I do that, I really have no idea how you actually sorted it. You could just use bubble sort, right? Or insertion sort. I mean, I do think that it can be helpful, and I'll just say this as a suggestion for people. It probably wouldn't be out of bounds in a programming interview for someone to ask you to implement a sorting algorithm. And they wouldn't say which one. They might just say, show me how you would sort something, right? Or just implement a sorting algorithm that you happen to know. And you're probably not going to get a lot of points for implementing bubble sort because it's pretty slow. You might want to know I wouldn't choose Quicksort either because the partition one's tough to get right. Merge sort is a pretty nice option because it's really, it's elegant, it's recursive. The merge is pretty straightforward from a programming perspective. I think it's probably easier to remember how to do merge than just to remember how to do partition. When I used to teach this class in front of a live audience, partition was like the one piece of code every semester that made me very nervous about getting right? It's like, I can fight my way through merge. I might make a few mistakes like I usually do, but partition, man, small mistakes in partition can be very hard to figure out what's going wrong. It's just kind of a strange process, right? It makes more sense to me every year that I teach it and every year that I think about it a little bit more, but I would practice that one before I got on stage because I would and I think sometimes I would even solve it and then have the solution like in another window somewhere just in case, right? Just in case I got stuck and didn't want to get totally wedged in front of 1,000 students. So, but anyway, yeah, I'm not sure I would rely on myself to know partition, but I think merge and merge sort are pretty good. And insertion sort's a perfectly fine sorting algorithm. It is used in certain cases because particularly for small arrays, insertion sort can be faster. Oh, hi. Jeez, it scared me. All right, the cat is here. Apparently, you seem to know when I'm doing these, huh? Okay. Yeah, so no, I wouldn't, but you might it's helpful just to have a few of these in your back pocket just so you can, impress your friends and neighbors. Any other? I'm gonna be here taking questions for another half hour. Since we're here and we're sort of having fun, I thought trying to figure out. So there's and I'm not saying that you use this algorithm because it's not considered. Let's see. I'll look at how to shuffle array in Java. Okay, collections.shuffle, that's what I'm going to do. So there's a fun, one of the complexity classes that we have not yet explored is n factorial. And part of the reason is there aren't very many good algorithms that are n factorial because n factorial grows really fast, like badly fast, like terrifyingly fast, like a rocket ship type fast. Hi, okay. But there is an interesting sorting algorithm that is this sort of, I think it's sometimes called BOGO sort, that you can implement that is O(n) factorial. So why don't we do that one because it's kind of fun. So I'll just grab this random playground. Please, bingo. Okay. So the idea with BOGO sort is that it's O(n) to test if an array is already sorted. And imagine that I have no way of doing any better than that. So all I could do is test an array is sorted. I can also shuffle arrays. I can shuffle arrays in O(n). And so what BOGO sort does is it essentially, the algorithm is the following. Shuffle all the elements in the array, see if it's sorted. If it's not sorted, shuffle the elements again, and continue this process until the array is sorted. So essentially, I'm making random guesses. I know how to verify, right? So I need an isSorted method. So let me see if this collections.shuffle method makes sense kind of right out of the box. Let's try, and again, if you have real questions, stop me, because I'm just amusing myself here. Let's see if it will shuffle an array. Oh, it wants a list. Okay, that's fine. We'll say list of integer values, and then we need arrays. So I'll use arrays.asList 1, 2, 5. Oh, and I need to be a list class too. All right, and then let's print it. All right, that seems to work. BOGO sort. Yeah, okay, so let's try it. So we'll say, so it's gonna have to return a list, I guess. Can I do, will this work? Let's see. Nope. Okay, so what I'll do is I'll say list integer BOGO sort, and it takes a list, and I don't need, this don't need to be integers, we could have it take a comparable. So it takes a list of comparables and values, and what I'm going to do. So here's what I'm going to do. The first thing I need to do is be able to test. So if the list is actually sorted, and so for that I'll just do my my classic approach here, which is I'm going to say if. So I'm going to write my loop. I'll say list of values dot size, because it's a list. Oh, and I'm going to go, I'm looking at pairs. I'm going to go up through the end. I'll say if values dot get I compare to values dot get I plus 1. If that is, so I came up with a nice way of remembering, a trick of remembering the compare to conventions. I think it has something to do with the actual directionality of the negative, the comparison operators you normally use, but I forgot it. Oh, hold on. I do remember. Okay, so if it's greater, then I'm going to break, because I found a case where it's not. Well, how about this? I'll say Boolean is sorted is equal to true, and I'll say is sorted is equal to false, and I'll break. If is sorted, I'll return. So at that point, the array is actually sorted. So let's try this. I need to have this in my back pocket somewhere. Otherwise, well, I'll put it right here, right? Otherwise, I'm going to shuffle the values. I'm going to keep doing this. And because we're not totally nuts, let's stick a print statement in there. So now we'll do BOGO sort values. Now what is that angry about? Oh, it's in a list of comparables. Why can it do this? Can I see if I can cast it here? Okay, that seems to work. Now this was already sorted, so let's put it in one that's not sorted. There we go. Yeah. so BOGO sort. Beautiful. And so now the question is, how many steps does this take? And so what I'll do is I'll initialize equals 0, and what I'm going to do is I'm going to count every time I have to do a comparison. And I'll return steps. And actually, this doesn't even really need to return a list. I'll just have it return an int. And because at this point I'm not going to stop until the list is sorted, so it's going to return steps. And what is it upset about? Oh, here we go. Return steps. Oh, and I don't want to return here. I want to return there. Okay. So you can see, this, it bounces around quite a bit. Sometimes I get lucky and it's sorted right away. So it looks like, so at that, it's interested to see how, let's print values. Okay, so there's 5. Yeah, okay, I see. So if I only have to go through it once, right? Then yeah. So there I check once to see if it's sorted. Yeah, but let's see how the goal here is to try to see how this grows, right? Because this is supposed to be factorial, right? And so now I'm not even sure this is going to finish. Oh no, it finished. Okay. So now it's like 66 steps. Let me not print the values here because that's taking up too much space. So 13, 26, 6, 20. I think the fact that, well, let's put some more interesting values in here. Okay, 9, 33, 50. Yeah, I think if we use distinct values, it's going to make this take a little bit longer because the pies are helping us. Okay, 165, 93, 636, right? It's pretty bad. Let's do this. Let's say, run it 1,000 times. Over, say, then steps is equal to sort values, and then if steps greater than max steps, we may need to run this fewer times because it may did I misspell this? Max steps. There we go. Okay. So yeah, so this is now, we're in the range of 2,000. I mean, there's still some randomness here, right? Okay, let's add one more value. So now we're going up to 6. Oh, now we're hitting the timeouts. Frequently, right? And so, with 2 values, we're talking about 14. With 3 values, now we're into the range of 30s. With 4 values, we're going to start to see something jumping up pretty quickly. With 5 values, now we're going to sometimes it's work 1,000, yeah. And then with 6 values, we're already off the charts. So this is not a particularly good sorting algorithm. Actually, it looks like 6 values. Oh no, but I've got duplicates again. The duplicates help. Let's see. Oh, this is already sorted. Okay, I can't do that. Let's put a 6 up here. I'll put the 1 back there. Yeah. Okay. There we go. So now you'll see that we're regularly over 10,000, right? So this is not a good sorting algorithm. It does work. Great question for the forum about the final midterm. Let's answer that there. That way everybody will see the results. All right. Other questions about sorting, about ways to... One of the things that I didn't show here is that where'd it go? Yeah, so the sorting algorithms, sort of the practical sorting, like the comparator, this approach, you can actually chain these together. I'm trying to figure out how to do that. There's a way to actually to express that I want to sort by multiple criteria. Let's see. That's one way to do it. There's a chain comparator. I think there's also yeah, there it is. Sort by area, then comparing. And so there's these ways to kind of build up these comparisons. If you want to sort by one key first, and then by another key afterwards. And so there's some pretty nice built-in functionality in Java to use this to support sort of common sorting patterns. So I would encourage you to kind of look into that when you encounter this as a problem in your own code. We've actually already seen this. You guys implemented a comparator way back in MP0, and that was an example of a case where rather than implementing a compare to method and the comparable interface, which is powerful, but it's also pretty rigid, right? I mean, it essentially says this is one way to sort this type of object, but it's the only way. Whereas in reality, frequently, particularly when we're working with data models, we want to sort things. Again, think about the UI for your MP. You might want to sort courses by department. You might want to sort them by name. You might want to sort them by the start time and the day. There's all sorts of different ways that you might want to sort of arrange that data for the user. So there's not really one sort compare to method that's going to work for all of these different use cases. So that's a great place where you would use something like a comparator. The library that we're using to render the list actually allows you to do that. So you essentially provided a comparator. And if you wanted to, I think you could actually change the comparators at runtime, and that could be a feature if people are interested in doing kind of a final project type extension to their MP. That could be an example of something you could do where you could essentially allow the user to select between different sort functions or sort approaches, and you could rearrange the list accordingly. It'd be kind of neat. Other questions about this sort of stuff? This is kind of, these method references are kind of cool too. Other questions? I think I saw a little bit of snow today. That was kind of exciting, I guess. I was kind of hoping we would make it all the way through November with no snow, but looks like didn't quite make it. I mean, there's like just a few flakes out there today. I mean, nothing substantial, but I'm pretty sure there was solid frozen, matter, solid frozen water of some kind falling from the sky and blowing in I don't know how you distinguish between sleet and freezing rain and snow, but what was out there today looked suspiciously like snow. And, it's about time. But anyway, almost made it to December with no snow, which is unusual. I'm trying to remember, last year or the year before, we had quite a bit of snow right around Thanksgiving. Actually, there was snow on the ground, and people saw photos from that. So, other questions while we're here together? All right, well, if there are no other questions, I think we can leave off a bit early today. It's fine with me. So this week, as promised, starting tomorrow, so we really have basically 3 lessons left. So tomorrow, Wednesday, Thursday. Friday's off to give some space to finish up MP2. Next Monday, we will devote the entire day. All of our sessions, there'll be no homework problem, there'll be no lesson. We'll devote the entire day to midterm review for the final midterm that's on Tuesday. There'll be no lesson that day, and then Wednesday I think I'll put up a little bit of stats about the course and things like that, and probably do office hours at some point to sort of wrap up. So that's the plan. So the next 3 lessons are the sort of promised bonus content. I'm not going to ruin the surprise, but they are, I think, pretty cool topics. Starting tomorrow, so I hope you guys enjoy those. The homework problems will continue, but the homework problems are continuing on themes we've already established. So there's no homework on these new topics that we're going to bring up over the next couple of days. Instead, the homework problems are still drawn from work with things like trees and sorting. We have a fun algorithms problem coming up. We have a couple of gnarly binary tree problems for you guys to enjoy, just to get some more practice with recursion and things like that. So anyway, hope you guys are all well. Okay. Somebody wanted I gotta look this up. I looked earlier, I think it was about 30%. Yeah, okay, let me do the calc here. Let's see here. Let me do the calculation. I guess I could show you guys this, but it doesn't really matter. What on earth? sorry. 28%. 28%. 28%. Oh yeah, you did fine. Oh, I should fix that at some point. 28% ISIS. So yeah, you guys got a long way to go. I think you can get there. There's usually some. I've done this in the past. There's just some peer pressure that needs to be applied. But yeah, the feedback's super useful. So please fill out the form when you have a chance. Let's see. Index for binary search. Why do you have to add -1? Doesn't it round it? Already, I'm not exactly sure what the question is. So there is a binary search solution walkthrough that I posted yesterday. I would encourage you to look at that. Let's see here. Depending on how you set up the binary search problem, the indices are always integers. The question is simply making sure that you don't skip. There's two problems that you can run into quite easily with binary search. One is that you skip values, and the other is that you examine the same value twice. And so, I would just kind of work this through, right? So, you find the midpoint, right? So you have the index at the midpoint. That's the value you're going to compare it to. So you're going to get that value. That's the only time you're allowed to retrieve that value from the list. If you retrieve it again, it's going to blow up. So at that point, you decide to go left or right, and you just need to make sure that the indices are set up properly to do that. The rounding that goes on when you actually compute the midpoint is not really that important, but you just have to make sure that you adjust the indices properly at every step. So yeah, go through the solution walkthrough. I think that'll help. I'll probably post another one with the recursive approach as well, because that's also a valid approach. So, all right, I will see everybody tomorrow.